So now let's go to analysis of clock sequential circuits. Analysis describes what a given circuit will do under certain operating conditions. So you were introduced to analysis of combinational circuits in Unit 3. Now this time, let's consider clock sequential circuits. So a certain logic diagram is considered as a clock sequential circuit if it includes flip-flops with clocked inputs. The flip-flops may be of any type, and the logic diagram may or may not include combinational logic gates. The behavior of a clock sequential circuit is determined from the inputs, the outputs, and the state of its flip-flops. For combinational circuits, we only consider the inputs and the outputs, but for sequential circuits in general, we consider the flip-flops and its state. The outputs in the next state are both a function of the inputs in the present state. So which means that the state in general would refer to both the present state of the flip-flops, and we are going to consider also the next states. The analysis of a sequential circuit consists of obtaining a table, also known as a state table, or a diagram, a state diagram, for the time sequence of inputs, outputs, and internal states. So we're going to have an example in the next few slides. So this is a summary of the procedure we're going to do in analysis. The first one is, the sequential circuit is given in the problem in any of these forms. So most likely, you would see a logic diagram or a circuit diagram. Sometimes you would see just the inputs of the flip-flops. And sometimes you have the state equation or the transition equation of how flip-flops would change from one state to the other. Next, we're going to derive the behavior of the circuit through a state table, also known as a transition table, and a state diagram. Now let's consider this first example. A sequential circuit with two D flip-flops A and B and an input X and output Y is specified by the following next state and output equations. So we have these two equations here as the next state equations, and we have this equation on the right as the output equation. So first, we need to draw the logic diagram of the circuit. Second is we derive the state table, and lastly, we derive the state diagram. So state equation is an algebraic expression that specifies the condition for a flip-flop state transition. So let's define these terms first. We have t plus 1 would mean time plus 1. So this denotes the next state of the flip-flop 1 clock edge later. And t would mean time or the present state. At plus 1, which is the next state for flip-flop A, is equal to A of t, x of t, plus b of t, x of t. So which means that this is referring to the present state, A and B, and this would mean the x of t means the present inputs. Next, we have bt plus 1, which means that this is the next state for flip-flop B. So we have here this equation as well. And lastly, we have here y of t, the present output y, and we have this equivalent expression. Now, notice that all variables in the Boolean expressions are a function of the present state. In other words, all of them have t here at the right side of our equation. So which means that they are all a function of the present state, and therefore we can omit the t after each variable for convenience, and we can express the state equations in a more compact form. So we have this here. On the left side, we remain it as is so that we would know that this would mean the next state. But on the right side, we have removed all the t's. So this becomes ax plus bx. The next state of b is equal to a prime x, and the output y is equal to a plus b, and the result is ANDed with x prime. So since the flip-flop inputs also determine the next state, so this is based from our D flip-flop characteristic table, which was introduced to you in the previous lecture. So we can say here that the input is just equal to the output, or in this particular case, the D input is equal to the next state. So we have this relationship. So since D flip-flop inputs would determine the next state, then the D inputs are the same as the next state equations, given that we have this relationship already. So that means that if these are the next state equations, then we can just equate that also to the D inputs. In this case, we call that dA and dB, the inputs of flip-flops A and B respectively. So now, based from our flip-flop inputs, wherein we have dA is equal to AX plus BX, and dB is equal to A prime X, the Y remains as is. So based from these three equations, we can now form our logic diagram. So I want you to take note of our two flip-flops here. So we have the flip-flops named as A and B, so which means that the present state or the output of the first flip-flop, we refer to that as A. And the second flip-flop, we refer to that as B. Okay, so the present state. They have equivalent complemented outputs also, the Q prime. So here we have the A prime and the B prime also on the second flip-flop. So to consider DA, DA means the input D of the first flip-flop. DB means the input B of the second flip-flop. So based on this equation, we can derive the dA input. So AX plus BX. So again, remember that A means the present state of A, which we can tap from the output or the Q output of the first flip-flop, which we have named A. So this would become input, the first input, ANDed with X. This is the external input here. We have this AND gate here. And then the second term, BX. So B comes from the present state of the second flip-flop we have here. So we have here, this is B, and ANDed with X. This forms the second term here. And both terms are ORed because of the plus sign here. Now, let's consider dB. So this is just simply A prime X. So again, A is the present state A, but since it already has a complemented output, we might as well use that one. So we have A prime ANDed with X. We just tap X here, and then that would become the value for dB. And finally, we have here our output function. We have Y is equal to A plus B, and the result is ANDed with X prime. So again, we are using the present states A and B. A and B here are tapped, and we are going to OR them together. Now this last part, there's an error to this one, so let me just correct this part at the output. So we have here Y is equal to A plus B. So both present state values of the flip-flops are ORed together, and the result is ANDed with X prime. That's why we have this one here. So this part is missing in the slide. So please take note of this correction. So after we have completed our logic diagram, now we can proceed to our state table. So a state table is just like a truth table, but with some other additional features specific for flip-flops. So technically it is defined as a time sequence of inputs, outputs, and flip-flop states. And this can be enumerated in this state table. So there are basically four sections. We have the present state, we have the input, the next state, and the output. So we can divide our truth table into half. On the left side, we have the present state. Since we have two flip-flops, we have here A and B. And since we only have one input, then we only have X here. On the right side, this is the next state. So we still have A and B here because again, we have two flip-flops and we only have one output Y here. To complete the state table, then we are going to use the equations that we have prepared earlier. So in preparing our state table, let us first prepare the left side of the table. So we have here the present state and the input. Now the three variables here would be A, B, and X. And since we have three variables, we have to create 2 to the 3, which is equal to 8 input combinations. So we have here the 8 combinations, starting from 0, 0, 0, 0, 0, 1, all the way up to 1, 1, 1. So this is just a faster way of creating the combinations. So anyway, let's move on. So on the right side, this is the next state, A and B, and this is the output Y. So we have here the following equations that would help us to complete the state table. So let's first consider our first equation. This is dA, but this is equal to the next state. This is the next state equation, and this is equal to ax plus bx. Now, since this is already in sum of products form, then it's easier for us to fill up our truth table. So by the way, our next state function is this part for a. Okay, so this means, I hope you remember your sum of products form. A and x are unprimed, so both of them have a value of 1, 1. Bx are also unprimed, so we have here values for both b and x, 1 and 1. So what we need to do is, if we first consider a and x, both a and x must be 1 so that we can have a 1 at our output here. So that means we have here 1 for a and 1 for x. So we have this combination. So this is 1, 1 and 1, and lastly 1 and 1 also here. Okay. Next we have b and x. So let's try to find where b and x are in our input combination. So we have here b, 1, x is 1, so we have that here. This is equal to 1. And lastly, we also have another one here. This is b is 1, x is 1, so we have this overlapping 1 at the output. So which means that since there are no other terms here, then the rest must be zeros. Okay, next let's proceed. B. So our next state for B is found here. So this is equal to a prime x. So since a is primed, a must be 0 and x unprimed must be equal to 1. So let's find that certain combination in our list of inputs. So we have a here, 0. So we have here, there are 4 of them. And x is 1. So we have here 1. Let's put an x. And next is 0, 1. We have another one here. Okay, no other terms left in our equation, so the rest must be zeros. Okay, and lastly we have y here. So this was our original function. We can distribute x prime into a plus b, so therefore we have this new y equation here. So a is unprimed, x is primed, b is unprimed, x is primed. Okay, so 1, 0 for our a and x respectively. So let's find that here. 1, 0. So we have 1, 0 here. So this one, this part. And what else? Here. 1, 0. Next, we have b x prime, 1, 0 as well. So we have here 1 and 0. So here. 1, 0. Where else? Here. 1, 0. Okay. So apologies for the slanting handwriting. So anyway, there you go. So no other terms left, so the rest must be zeros. Okay, so what we do now is we verify this with our table here, original table. So I guess this is correct. We have lastly, okay, there you go. So I hope you were able to follow. So sometimes it is convenient to express the state table in a slightly different form by having 3 sections: present state, next state, and input. So this was our state table derived from the previous slide. So we have the 4 sections or the 4 columns here. But on the right side, this is another representation or another way to write our state table. So we just put the present state on the left side, and on the right side, we incorporate the values of our inputs, 0 and 1 in this case, and we have two columns for our next state, a total of 4 because we have two flip-flops, and we divide this one into x is 0 and x is 1. So basically, it's the same information within, but we have different representation. So one form may be preferable to the other, and this depends on the application. Okay, so how do we analyze a state table? So here, this means that if our present state is 0, 0 for A and B, then the next state would become 0, 0. So that means unchanged if x is 0. And if x is 0, the output also is 0. If present state is 0, 0, the next state would become 0, 1 if our present input x is equal to 1, and correspondingly its output is 0, and so on. So we have our next requirement, a state diagram here. So the information in a state table can be represented graphically in a state diagram. So basically, there's no difference between a state table and a state diagram except in the manner of representation. So the state table is easier to derive given from a logic diagram and the state equation. And the state diagram follows directly from the state table. So this is just a graphical view or a pictorial view of the state transitions. And it's easier for humans to understand this one. So I think this was introduced in the previous lecture, a state diagram for the flip-flops. But in this case, we're going to consider a combination of flip-flops because in this particular example, we have two of them. So let's just recap the symbols that we use. We have a circle to represent the state. So in this case, we are going to consider combinations of our flip-flops. So we have here state AB 0, 0, 0, 1, 1, 0, and 1, 1. So which means there are 4 circles here in our diagram. So the binary number, or sometimes its symbol, would mean the present state of the flip-flops. So here 0, 0, 0, 1, 1, 0, 1, 1. So you can rearrange the circles in any way you want. The arrows would represent the clock-triggered state transitions. So when does your sequential circuit change its states? So it depends on the conditions we have on our arrows. And we have here some other symbols. We have x/y. The left number in the slash are the inputs, or is the input. In this case, there's only one input, so we have only one variable here, x/y. The right side of the slash are the outputs, but in this case, we only have one. That's why we only have y, and that is what it means here. So basically, if you follow the state diagram, if you are in state 0, 0, you retain that state in the next clock cycle if your input is 0 and correspondingly its output is 0. That is based from the state table. Okay, 0, 0 goes back to 0, 0 if input is 0 and the output is 0 rather. It goes to state, consider the direction of the arrows, 0, 1. So here it goes to state 0, 1 if the input is 1. So we have this arrow here going to this state 1/0 and 0 on the right side of the slash because the corresponding output here is 0. And you derive the rest from the state table again. So we have here this state diagram. So let's consider the summary of what we did in example 1. So we were given state equations. Since we are using D flip-flops, and from the state equations, we can derive the D inputs. So we can use that to create our logic diagram. After we have the logic diagram, we still use the state equations to complete our state table. And from the state table, we can have a state diagram. So if you're going to analyze and consider the transitions of the different states in the state diagram, you can see here that the output would become 1 if you are in states 0, 1, 1, 1, or 1, 0, and the input is 0. Okay, so which means that this circuit is a 0 detector. So it asserts the output y is equal to 1 when a 0 is detected in a stream of 1s. So in the case of state 0, 0, the output is 0 because state 0, 0 represents the first or the initial state, which means that there is no input yet. But once the input becomes 1, input is 1, the next state is 0, 1. So which means that there is already an input coming into the circuit. So if you are in states 0, 1, 1, 0, and 1, 1, then that means there is already a presence of 1 in our stream of inputs. So that's why the output would only become 1 if you are in these three states and an input of 0 is being detected. Now let's go to the second example. So here we're going to consider the analysis of flip-flops other than the D flip-flops. So remember in example 1, we were using D flip-flops, and this flip-flop is special because the D input is just equal to the next state value, therefore making the process a little bit easier. So this time, let's have two JK flip-flops. So we have a sequential circuit with two JK flip-flops A and B and one input X. The logic diagram of the circuit is shown below. Derive the state table and the state diagram of the circuit. So this is the given logic diagram. So unlike example 1, we were deriving the logic diagram based on the next state equations. This time we were given a logic diagram. So first, we must take the flip-flop inputs. So based from the logic diagram, we can trace the connections. And we have the two flip-flops here. The output for the first one is A, the present state A. And the second output the second flip-flop has its current state or present state B. So here, we can see that JA, or the input for J input, comes from these connections. We have B here. B is directly connected to J. So that's why we have JA is equal to B. The K input for A flip-flop, or let's call that KA, is coming from this one. So X prime and B, or BX prime. And that would become the input for KA. For the second flip-flop, so this is JB now. JB comes from X prime and KB comes from AX or X, and we can rewrite that in its sum of products form. By the way, for logic diagrams having flip-flops, you must remember to connect the clock inputs to a clock source. This is very important. So in this case, we can just connect both clock inputs to the same clock source. So again, unlike the D flip-flops, the other type of flip-flops such as JK, T flip-flops, and maybe SR flip-flops also, the D flip-flop has this particular special relationship between the next state and the D input. However, when other flip-flops are used, we need to add flip-flop inputs. And this is because we use the flip-flop inputs to derive the next state values. In the case of using JK flip-flops, then we need to add the flip-flop inputs here. So since we have two flip-flops, A and B, we will also have inputs J and K for flip-flop A, and the two inputs J and K for flip-flop B. So a total of 4 additional columns here. Now technically, the columns labeled flip-flop inputs are not part of the state table, but we need these columns so that we can derive the next state. So before we proceed, let's try to derive where the flip-flop inputs come from. So let's start with the blank state table. So we have the equations written here. This is the inputs for flip-flop A, and these are the inputs for flip-flop B. Since we don't have an output for this particular example, then we don't have an output table here or maybe somewhere here. So just like the D flip-flops, we need to fill out the left side for the present state and the inputs. In this case, we have two flip-flops A, B, and we have one input X. So that means we have 3 variables, 2 to the power of 3. We have 8 combinations for our inputs from 0, 0, 0 up to 1, 1, 1. So we cannot derive the next state right away. So let's just leave that blank for now. But we can fill out the flip-flop inputs based from the equations. Okay, so let's start with JA. So the J input of flip-flop A, which is just equal to B. So which means that we just simply follow the values of B into our JA column. So this means this is 0, 0. This is 1, 1. 0, 0, 1, 1. We are just following this column. Next, KA. So this is equal to BX prime. So we can use the sum of minterms notation. This is 1 and this is 0. And we find BX combination. That is 1 and 0. So we have this one part, 1, 0. That means this is a 1. And we have another one here. And the rest are now zeros. Next, let's consider the other flip-flop. So this is equal to X prime. So we just need to complement X. It's 1, 0, 1, 0, 1, 0, 1, 0. And finally, the last input for flip-flop B, which is KB. So this is equal to AX or X. You can evaluate this one if it's easier for you, or you can evaluate it in its sum of products form. So I'll choose this one. This is 0, 1, and this is 1, 0. So 0, 1 for A and X. So we have A here and X here. So A and X must be 0, 1. So we have here 0, 1 here. And the next one is 1, 0 for A and X still. So 1, 0, 1, 0. And the rest would be zeros. So this completes our flip-flop inputs column. So this is just to briefly verify our recently filled out table. So once we have filled out the flip-flop inputs, now we are ready for the next step. So here, we use the flip-flop inputs to determine the next state values. And since we are not using D flip-flops, then we need to consider the flip-flop characteristic table. So let's pull out the JK flip-flop characteristic table. So again, the next state values, the one here and this in the middle of the state table, are determined using the flip-flop inputs. So what we're going to do here is we look at the JK inputs found here. So we look at a pair J and K for flip-flop A, and we consider what is the next state value based on this characteristic table and fill out this part of the table. So let's go back to our partially filled state table. So this is just a lookup table, the characteristic table that we're going to use. So I hope it's not too small. So anyway, 0, 0 is no change. 0, 1 is reset. 1, 0 is set. And 1, 1 is complement. So again, we consider the J and the K inputs, and we fill out this part, the A column for the next state. So if J and K are 0, 0, then our next state is no change. So which means we follow whatever the present state value of A. So we look at A and J and K inputs for A. So since this is 0, 0, so no change. So 0 remains 0 on the next state. Next, this is still 0, 0. So we just follow the present value. Next, 1, 1 means complement. So we look at present state A and we complement or we toggle. Next, this is 1, 0, which means this is set. So set means the output directly is 1, or the next state value is 1, regardless of this value. Next, 0, 0 is no change, so we just follow the present state values. 1, 1 is complement, so 1 here from the present state becomes a 0 on the next state. And finally, 1, 0 for JK, 1, 0 is set, so that means this is 1. So to briefly check our inputs, so we have 0, 0, okay. So once next state for A is complete, we are now ready for flip-flop B. So to continue, now let's consider flip-flop B, inputs J and K, and we are going to fill out this column here. So again, referring to the characteristic table, this is 1, 0, so that means this next state is set, so that is 1. 0, 1 means reset, so 0. 1, 0 is set, 0, 1 is reset. This is 1, 1, which means complement. So we look at B. So this is B here. 0 becomes a 1 at the next state. Next, 0, 0 is no change. So from 0, it is still 0. This is complement. So 1 becomes a 0. 0, 0 is no change. So 1 is still a 1 at the next state. So briefly looking at our B column here, cross-reference that to our slide. Okay, so I guess this is correct. So our state table is now complete. So the next step is to derive the state diagram. So again, the state diagram is just the same information as we have with the state table. So let's consider present state 0, 0 first. So let's have this state here, 0, 0. So if x is 0, the next state is 0, 1 if the input is 0. So here goes to 0, 1. So take note that we don't have a slash and a number here because this example does not have any outputs. So the directed lines just represents the input. So next is if 0, 0 is a present state and input is 1, it goes back to the same state. So that's why we have this arrow returning back to itself. Considering the next state, 0, 1, it goes two ways. It goes to 1, 1 if the input is 0, so here. And if the input is 1, it goes to 1, 0, which is here. And we can derive the rest using these two columns here. So as a summary of the steps we have done in example 2, we have first the logic diagram. So from the logic diagram, we were able to derive the flip-flop inputs by tracing the circuit. So once we have the flip-flop inputs, we use the characteristic table so that we can create or complete the state table. And finally, once we have the state table, we can interpret that in a state diagram, which we have here. In this particular case, if you analyze how the states change in relation to the inputs, so the circuit follows a certain sequence and it is based on the input x. So if x is 0, the sequence is from 0, 0, it goes to 0, 1, and then it goes to 1, 1, and then it goes back to 0, 0. So it just repeats 0, 1, 3, and it repeats. In the event that we are in state 1, 0, if x is 0, the state goes to 1, 1. So if this is the present state, if the input is still 0, it goes to 1, 1, and the sequence will repeat. When x is 1, states 0, 0, 1, 0, and 1, 1 will retain their current states, which means that no change is happening. So here it goes back to itself, this goes back to itself, and 1, 0 also goes back to itself. When x is 1, state 0, 1 goes to state 1, 0. So this is the summary of the sequence or the behavior of example number 2. So this is the end of our lecture. So please answer the exercise after this, and thank you for watching. Have a great day.